Mingalava, welcome back to Machine Learning course. Today, in the previous lesson, we talked about the regression, especially the linear regression, simple linear regression. Right. So, in these videos, we are going to learn about multiple linear regressions. In a linear regressions, the target value is predicted using only one independent variables. For example, the price of the car is predicted using only the car engine size. However, the price of the car is not the price of the car is dependent not only on the engine size, but also on the other features such as like car models, brands, the mileage that the car has driven. So in multiple linear regression, the model is built using the multiple features, right? And there are more than two coefficients to be estimated from the models. So in multiple linear regression, the underlying assumption is features are not highly independent variables are not highly correlated to each other. That's why here each the target value is correlated to dependent on the each individual features, and then each individual feature is combined using a linear equations. Right. So with this, we can use the linear regression techniques to find the parameters by minimizing the loss function that we discussed earlier. Right? So in linear regression, we try to fit the training data using a single line, straight line. All right. However, this can lead to underfitting problems where the model is too generalized, right? So this does not even fit to all the data points in the given training data sets. So here we talk about the polynomial regression. In polynomial regression, instead of using a straight line to fit the training data, these methods use a curve to fit the training data points. So the target value is predicted using a nonlinear equation, right? So if we want to fit a parabolic to the data instead of a straight line, we can combine the features in the second order polynomial equation, like given as y equal to a plus b1 x plus b2 x squared. All right. So likewise, we can model the using the higher orders and the order of the equation, and the number of parameters to be estimated will increase as the number of orders increases. Right. A polynomial regression is not only for a single feature, it can also be used for multiple features. This is a one example of multiple polynomial regression equation. Right? So here you can see that we have only two features, but we have six tens if we are using the second order polynomial equation. Right? If we are using that polynomial equation, we will have more features and more parameters. So it looks complex, right? But one good news is that we still can perform this as a linear model by transforming the feature into a new dimensional space. Let's look at one particular example with two features and second order polynomial equation. Using two features with the second order polynomial equation, we have six parameters. A1, B1, B2, B3, B4, and B5. All right. And this is a polynomial equation. It's a second order polynomial equation. We can see that we have a x1 square, x2 square, and x1 x2. But don't worry, we can transform this into a new dimension called z. All right. So if we assign x1 as z1, x2 as z2, x1, x2 as z3, x1 square as z4, and x2 square as z5, we can redrive the equation y in the z space as a1 plus b1 z1, b2 z2, b3 z3, and so on. Obviously, this y and z give you a linear equation. All right. So the parameters can be estimated by the same techniques we use in linear regression model. So in summaries, linear regression models linear regression models a relationship using a linear equation. In polynomial regression, the model is built using our nonlinear regressions. In polynomial regression, polynomial transform is used to transform from nonlinear equation to linear equation. Then least square method, which is used for linear regression, is also can be used for polynomial regression to find the coefficient that provide the minimal least square errors between the predicted and accurate values. All right. But one known issue with the least square method is overfitting, where the model is fitted well to the training data set, but it is not generalized enough to predict the new data sets. So to address this issue, the regularized regression methods introduce a new term in the loss function to regularize the size of coefficients. In Lasso regression, the regularized terms introduce the magnitude of coefficients as shown in the equation alpha omega I, right? Magnitude of coefficients. In the rate regressions, the regularized terms use the square of coefficient. That's why rate regression is sometimes also called as L2 regression, whereas Lasso is called as L1 regressions. Both Lasso and rate regression reduce the model complexity and corollary, right? Which is dependency between features. Here, lasso regression can also be used as a feature selection tool because less important features are eliminated when the regularitors become larger and larger. So, regularized regression is used to um, reduce the effect of overfitting. In the next videos, we are going to learn how to develop these machine learning models using the scikit-learn library, which is the most popular library for supervised learning. See you all in the next video. Thank you.